Right now, a regular computer would take 10,000 years to solve a problem that a quantum computer could crack in just 4 minutes. Imagine that scale of exponential power. That same machine, once fully realized, could break into every bank account, every nuclear launch code, and every encrypted secret on Earth. It's not science fiction, it's a technological reality governments are racing to build, and the implications are staggering. We're talking about a shift in global power, a transformation of security, and the dawn of capabilities we can barely grasp. This isn't just about faster calculations, it's about fundamentally altering what's possible in the digital realm. Every piece of encrypted data we currently rely on, from your online banking to critical national infrastructure, military communications, and even state secrets, could become instantly vulnerable. The very foundations of our digital security, built on complex mathematical problems classical computers can't solve quickly, crumble in the face of quantum power. This unseen threat looms large, driving nations into a high-stakes, covert competition. This isn't a future problem, it's a present race. Governments and tech giants are pouring billions into developing these machines, not just for scientific curiosity, but for a decisive strategic advantage. The nation that first achieves true quantum supremacy will wield unprecedented power, capable of decrypting rivals' communications, designing unbreakable codes, and innovating at a speed previously unimaginable. The quantum race is the quietest, yet potentially most impactful, arms race of our generation, and its outcome will reshape global geopolitics. To understand this power, we need to go back to basics. Traditional, or classical, computers operate using bits. A bit is a fundamental unit of information that can exist in one of two states, either a 0 or a 1. Think of it like a light switch that's either on or off. All the complex operations our computers perform, from streaming video to financial modeling, are built upon these simple binary choices. But quantum computers introduce a revolutionary concept, the qubit. Unlike a classical bit, a qubit can exist in a superposition of states. This means it can be both 0 and 1 simultaneously, or any combination in between. Imagine a spinning coin. While it's in the air, it's neither heads nor tails, but a combination of both possibilities until it lands. This ability for qubits to inhabit multiple states at once allows quantum computers to process vast amounts of information in parallel, dramatically increasing their computational capacity compared to classical systems. Even more mind-bending is entanglement. When two or more qubits become entangled, they become interconnected in such a way that the state of one instantly influences the state of the others, regardless of the distance between them. It's as if they share an invisible, instantaneous link. This bizarre quantum phenomenon allows entangled qubits to work together on incredibly complex problems, enabling exponential increases in processing power that are simply impossible for classical machines. The first significant milestone in this race was Google's announcement in 2019. Their Sycamore processor, equipped with 53 qubits, achieved what they termed quantum advantage. It performed a highly specific calculation in just 200 seconds, a task that Google estimated would take the world's most powerful supercomputer approximately 10,000 years. This wasn't a general-purpose computer, but it was undeniable proof of quantum computing's potential to transcend classical limits. While groundbreaking, it's crucial to understand that quantum advantage for Google's Sycamore was achieved on a very specific, carefully designed problem. It's not yet capable of solving any problem faster than a classical computer. Think of it as a specialized calculator that can do one incredibly difficult sum much quicker than any human or traditional calculator. But this proof of concept confirmed that quantum computing is not just theoretical, it's a tangible, albeit nascent, technology with incredible promise. This breakthrough ignited an even fiercer geopolitical scramble. The race for quantum supremacy isn't just about scientific prestige, it's about national security and economic dominance. The ability to break virtually any current encryption or to design new materials with unprecedented properties represents a seismic shift in global power dynamics. Nations are now competing to develop their own quantum capabilities, understanding that whoever leads in quantum will shape the future of technology and global influence. The United States government recognizes the strategic imperative of this race. In 2023 alone, it allocated an impressive $1.2 billion towards quantum research and development. This investment spans across various federal agencies, universities, and private sector partnerships aiming to foster innovation, build a skilled quantum workforce, and ensure America's leadership in this critical technological frontier. It's a clear signal that the U.S. views quantum computing as a cornerstone of future national security and economic prosperity. However, China has made an even more aggressive bet. Over just 5 years, from 2017 to 2022, China invested an estimated $15 billion into its quantum research programs. This massive commitment includes the construction of the National Laboratory for Quantum Information Sciences, a colossal facility dedicated to advancing quantum technologies. This investment underscores China's ambition to become the world leader in quantum computing, aiming for a decisive edge in scientific research, military applications, and economic growth. The stakes for national security are immense. Imagine a world where all current encryption standards are obsolete. Military communications, intelligence gathering, and secure data storage would be compromised. The nation with superior quantum capabilities could gain unparalleled access to adversaries' secrets, while protecting its own. This potential to achieve information dominance is why quantum computing is not merely an academic pursuit, but a critical component of strategic defense and offense for major global powers. While the security implications are profound, quantum computers promise breakthroughs far beyond code-breaking. Consider drug discovery. Simulating how molecules interact at an atomic level is incredibly complex, even for supercomputers. Quantum computers, with their ability to model subatomic behavior, could revolutionize pharmaceutical research. They could rapidly screen billions of potential drug compounds, predict their effectiveness, and design new medicines with unprecedented precision, accelerating the development of treatments for currently incurable diseases. The impact extends further into materials science, where quantum computers could design novel materials with tailored properties, perhaps superconductors that work at room temperature, or super-efficient batteries. In finance, they could optimize complex portfolios and detect fraud with unmatched accuracy. Their ability to solve previously intractable optimization problems will transform logistics, supply chain management, and even climate modeling, unlocking efficiencies and insights currently beyond our reach. Quantum computing also holds the key to unlocking the next generation of artificial intelligence and machine learning. Training complex AI models requires immense computational power and the ability to process vast datasets. Quantum algorithms could dramatically accelerate this process, enabling AI to learn from more data, identify subtler patterns, and make more sophisticated predictions. This synergy could lead to truly transformative AI systems, from personalized medicine to autonomous systems that think and react with human-like intuition. Here's a chilling scenario: even though widespread quantum decryption isn't yet feasible, adversaries could be secretly collecting vast amounts of encrypted data today. This practice is known as harvest now, decrypt later. They stockpile this data, anticipating the day a sufficiently powerful quantum computer becomes available. When that day arrives, all that previously secure information, state secrets, personal data, financial records, could be retroactively decrypted, posing an unprecedented threat to privacy and national security. Recognizing this looming threat, governments and major tech companies are not standing idly by. They are actively engaged in developing post-quantum cryptography. This involves designing new encryption algorithms that are resistant to attacks from even the most powerful quantum computers. It's a race against time, as the world transitions its digital infrastructure to these new, quantum-safe standards, ensuring our information remains protected in the quantum era. The U.S. National Institute of Standards and Technology, or NIST, is at the forefront of this effort. They launched a global competition to identify and standardize the most robust post-quantum cryptographic algorithms. After years of rigorous evaluation, NIST has selected candidates like Crystal's dilithium and Crystal's Kyber as future standards. These algorithms are designed to secure everything from digital signatures to encrypted communications, forming the backbone of the Internet's future defenses against quantum attacks. So, how close are we to these game-changing machines? While specialized quantum computers exist, practical, fault-tolerant quantum computers capable of general-purpose, widespread use are still estimated to be 10 to 20 years away. This isn't an overnight revolution. There are significant engineering challenges to overcome, from maintaining qubit stability to scaling up the number of qubits while minimizing errors. Yet, the foundational breakthroughs are happening now, paving the way for a future unlike any we've known. The quantum race is more than a technological competition, it's a struggle to redefine global power, economic leadership, and scientific progress. The nation or entity that masters quantum computing first will have an unparalleled advantage in defense, intelligence, healthcare, and finance. It promises a future of incredible innovation and prosperity, but also one with profound security challenges and the potential for unprecedented disruption. This is why the silent quantum race commands such urgent attention. The implications are clear: quantum computing will fundamentally change everything we know about technology, security, and even reality itself. The race is on, with nations investing billions, driven by both the promise of untold progress and the threat of catastrophic vulnerability. The winner will hold the keys to a new era, dictating the pace of scientific discovery, securing global communications, and reshaping the balance of power for generations to come. The question isn't if quantum will change the world, but who will write its future.